Back in the airport again. So with this question, question 5 is another one that's on the easy side, I'd say. You just have to be calm and have practiced manipulating tensor indices, which is, again, something that seems perfectly reasonable for somebody who's been studying general relativity for a term. Part A, what you do is you write the delta function with prime coordinates as a partial derivative of x alpha prime with respect to x beta primed, and then you insert the Lorentz boost partial derivatives between the unprimed and the prime coordinate systems between alpha primed and some new index I've used mu, and beta primed and some new index I've used lambda, and that leaves your residual partial x mu with respect to partial x lambda. But that's just delta mu lambda, and if you write it that way and then take a step back and look at what you've got, you've just proved that delta transforms as a tensor of rank 1, because that sequence of partial derivatives is exactly a transformation you expect of such an object. So in part B, you are left with a product of epsilon with 4 indices, and it's totally antisymmetric, and A, 4 copies of A, each with a different index matching one of the indices in the epsilon object. And the way you prove that that has to be 0 mathematically is you switch 2 of the indices. Of course, you have to do it consistently, so you have to switch the indices both on the epsilon and between the A's. So first thing you can do is write down epsilon alpha beta gamma delta A alpha beta A gamma A delta equals epsilon alpha beta gamma delta A alpha A beta A gamma A delta. And then you just switch the indices alpha and beta. So the right hand side becomes epsilon beta alpha gamma delta A beta A alpha A gamma A delta. Now, however, you can use the symmetries of the objects involved, so the A's you can just swap back again because they commute, so you end up on the right hand side with A alpha, A beta, A gamma, A delta. When you switch the alpha and the beta on the epsilon on the right hand side, you go from epsilon beta alpha gamma delta to minus epsilon alpha beta gamma delta. So now you have epsilon alpha beta gamma delta, A alpha, A beta, A gamma, A delta equals minus epsilon alpha beta gamma delta, A alpha, A beta, A gamma, A delta. And if something is equal to minus itself, then it must be 0. So that's a nice rigorous way of showing that the symmetric product of A's times the antisymmetric tensor epsilon is naught. So the next part confused some people last year. I actually want something very, very simple out of this part. This is just trying to show the tensorial character of epsilon alpha beta gamma delta. So you could do this one using the result from part B, which says that epsilon alpha beta gamma delta A alpha A beta A gamma A delta equals 0. Now each of the A objects is a tensor of rank 1, 0, and 0 on the other side of the equal sign is a tensor of rank 0, 0. 0 transformed in any other coordinate system is 0. So the remaining object, epsilon sub alpha beta gamma delta, must be a tensor of rank 0, 4 for consistency in the equation, and that's all I want for this part. So part D, again, is very neat and quick. You don't have to use a whole load of heavy machinery. If you start out with epsilon sub alpha, beta, gamma, delta, then alpha, beta, gamma, and delta all have to be different. If any two of them are the same, it's an antisymmetric tensor, so that object with two indices is the same as 0. So if they're all different, it stands to reason that one of them has to be 0, another one has to be 1, another one has to be 2, another one has to be 3. Now, you've got to raise all those indices in turn using the raising operator, which in flat space is a to mu nu, which is a minus 1 in the 0, 0 component and a 1 in all the others. So as a result of that single minus 1, you will get a sign flip when you raise those 4 indices in turn, because 3 of the raisings will not induce a sign change and 1 of them will. Now, if that's true in flat space, then when you go to a curved space or a curvilinear coordinate system, your a to mu nu's become g mu nu's, and now you have a tensor way of raising the operator and raising epsilon mu gamma delta. And if it's true that you get a minus sign when you raise all the indices in flat space, it must be true that you get a minus sign when you raise all the indices in curved space too. So it's one of these tensor generalization arguments that I've made quite often. That's all you have to say to get part D right. And the final part is also sort of arm-waving type index argument. So we start by setting beta equals 1, gamma equals 2, and delta equals 3. Now the only way that you can have anything other than zeros for these epsilon objects is if the nu and the alpha are both 0. Otherwise, one of these objects is going to be 0. So you've got epsilon sub 0, 1, 2, 3 times epsilon super 0, 1, 2, 3, which has to be minus 1. Any other result, and that product is 0. And so therefore, the product of these two epsilons is delta mu alpha, expressing the fact that they have to be equal, times minus, because the minus sign occurs because your upstairs and downstairs versions of epsilon 0, 1, 2, 3 have a relative minus sign between them. Now, of course, we picked beta equals 1, gamma equals 2, and delta equals 3, but you could have picked any combination. If we started with those particular choices, in order to get any other set of choices, we have to simultaneously permute the same index pairs on the upstairs and the downstairs objects. And when we do that, we never get anything other than a plus sign, because both objects will get a minus sign under the exchange of pairs of indices, and those two minus signs multiply to give plus 1. So once you've proved that epsilon sub 0, 1, 2, 3 times epsilon super 0, 1, 2, 3 is minus 1, then all the other possibilities are true as well, because of that symmetry, exchange of pairs of indices. So that's the end of this exam paper. I think this exam paper is a really object lesson in reading through the whole paper, because in fact the hardest questions were the compulsory question and the first two non-compulsory questions. The easy questions were the last two. So the students who attacked those questions probably would have done better. In reality, actually quite a few students tried the very last question, even though it really wasn't that difficult, and probably quicker certainly than the question 3 was, and less sort of cerebral in question 2. Anyway, look, very good luck on the exam. I believe you have to check where the exam is. It's of course likely that it isn't in a convenient place. It may even be at the Sheffield Wednesday football ground. So do give yourself enough time to get there. Bear in mind that trams will be crowded because there are many students trying to go to the exam. So give yourself some extra time, and give yourself plenty of sleep the night before the exam as well. This is not an easy subject, so having your wits about you when you're trying to do your questions is absolutely vital. Do send me an email if you have questions about anything else. I'm trying to get through marking and sending you back problem set 2. I'll try and get that done in plenty of time so that you've got those to look at well before the exam on the 27th. Okay, bye.